talk about boundary dynamics of wandering domains overview. Thank you, Gwyneth.
Okay, thank you, Letitia, and thank you very much for the invitation to speak. It's great to see people in a room together, and I'm sorry not to be able to be there with you, but it's great to be able to join in from here and look forward to seeing people in person again at some point. So this is the first of 3 talks on this work, and I also should apologise if people were in the talk in Germany last week with my talks. Basically the same talk as I gave last week, but then it'll be followed by more details about some of the proofs and examples in the talks that Phil and Fatou are giving after this one. And I should also apologise in case I disappeared. So our internet has been playing up a little bit this morning, so it was dropping out for a few minutes. It did come back. So if I disappear, hopefully I will come back again. But, we'll hope that doesn't. Okay, so what I want to talk about is joint work with lots of people. So it's been a really good project to be involved in, and so it was with Anna, Fatou, Nuria, and Phil. And actually, we realised that one of the having got used to using Zoom and things, it's been great for collaborating. Even though they're sort of spread around in different countries. So Nuria and Fatou were there, so if there were questions and things, they can certainly pick them up kind of in person, so to speak. Okay, so I will start talking about what the work is all about. If I can get my screen to work. Right. Okay. Yeah. Okay, sorry, Phil's just checking my internet's working, I think. Okay, okay, so Andrew's just appeared in the background, okay. Right. So what I'm talking about is wandering domains, which are a type of component of the Fatou set, and I think this is the first of many talks on wandering domains, but because I'm the first one, I'll give some of the background. So we're looking at the components of the Fatou set, and the functions which we're looking at for this talk, we're looking at transcendental entire functions. So we have this function mapping the complex plane to itself. And if we have a Fatou component U, then we're going to use UN to denote the Fatou component containing F to the n of U. So we have this picture here. We have a Fatou component U mapped to U1, mapped to U2, mapped to UN, and so on and so on. If they're bounded like I've drawn here, then actually U will map onto U1 and so on. But if you have an unbounded Fatou component, you may omit a point when you map forwards. But this is the setup we're interested in. And as I'm sure you all know, we have a situation, you could have a situation where you have a periodic Fatou component, so that you eventually map back into the Fatou component that you started off in. Or you could have a pre-periodic one where you map forward for a few steps and then you map into some cycle. And then we have the case that I want to talk about today, which is wandering domains. When each stage of this picture here, every component is different to any others. You never come back to the same place. So the periodic ones we have a really, really good understanding on. So we have this really nice classification going right back to sort of Fatou and Kramer back in the 1920s. And we have a really precise description of the dynamics inside these Fatou components, and that's fantastic. And also for rational functions, we have this big result by Sullivan, which says that there are no wandering domains. So for rational functions, the only ones we need to worry about are these periodic Fatou components, which we understand really well. But one of the sort of really nice, interesting differences when you get to transcendental dynamics is that we have these wandering domains, and there's a whole another world out there of kind of interesting behaviours that can happen. Okay, so the first examples of wandering domains were actually multiply connected ones, and these were due to my supervisor Noel Baker back in 1976, when the world wasn't so interested in complex dynamics, but he was proving all these really, really interesting results. And actually, the first example he constructed over, there was quite a big gap. There was sort of 2 papers. The first one showing that he had sort of ring domains which mapped out, and then actually several years later showing that these were actually in separate Fatou components. They were definitely wandering domains. And the example he gave was an infinite product. So it's not a kind of a function you could write down very easily in terms of a nice simple formula like an exponential or something. It was this carefully constructed infinite product where you put the zeros in the right place to give you the type of behavior that you want. And then having done that, he then put this really, really nice theorem, which said that whenever you have a multiply connected Fatou component, as soon as you've got a hold in your Fatou component, then it will always be a one-ring domain. So when we have loads of one-ring domains, and actually he proved much more than that they have a very similar type of behaviour. So that for large N, we have this picture here, so that you'll want to make them wander around for a bit, but then it will always get it map into this sequence of ring-like domains with, so we've got one here that maps out to the next one out here, which will map out to a bigger one out here, which will map out to a bigger one, and so on, and they'll go off to infinity. So this is really, really nice. As soon as you have a hold in your Fatou component, you know that after a certain number of steps, you'll have this type of behaviour. And various people have studied the dynamics inside these multiply connected Fatou components. We have a big paper with, so Phil and myself, with Walter Bergweiler, who was just talking. And this gives you a detailed description of what happens inside your one domains, a bit like you have inside the periodic Fatou components. So you can see here they could be very irregular, you can have lots of holes, but what we showed was that inside each of these there's going to be a big round, proper round annulus, and you get this sequence of absorbing annuli, and even however irregular your one domain is, kind of every point in your one domain will eventually get sucked into this sort of big annulus in the middle of your one domain, and then it will stay in there. And within that big round annulus, we also show that the function behaves like a large degree monomial, with the degree getting bigger as n gets bigger. So as you get out, you get higher and higher degree monomials there. So you can have all these holes and things. You can have infinitely many holes, you can have no holes. If you have finitely many holes, that number will drop at each, eventually going down. So you just have a doubly connected one. So there's lots you can say about these multiply connected ones. So what might have started off of looking at a complicated situation actually turns out for entire functions, and it's very different from meromorphic ones, but for entire functions, you have this really, really nice behavior. So that was the background to the project that I'm talking about, this joint work with the 5 of us working together. So we have nice description of the periodic ones, you have a nice description of the multiply connected ones, but what about simply connected ones, which might sound simpler, but it turns out that actually all kinds of different things can happen. Okay, so just a sort of little background in what can happen in terms of the orbits of the simply connected one ring domain. So we saw for the multiply connected ones, they map out into these rings that go off to infinity. But what can happen if you have a semi-connected one? So you have 3 different possibilities that can occur. Okay, so the first one is escaping, which is what we had for the multiply connected ones, that each point in the one domain will escape to infinity. And this is what most of the examples of one domains that are out there will look like. So and actually the sort of classical examples of the things, like so the first example, which is due to Herman and things, they're basically escaping versions of periodic components. So you can construct these using lifts and things, and so you can have things that look like periodic ones, but they're moving along. Harder to construct is this type. So you have oscillating ones, or okay, so when you look at these, you might think, oh, maybe all escaping one remains are escaping versions of the periodic ones, and then I think life would be very simple. But actually, that's not the case. You can get all kinds of interesting behaviour, lots more different types of behaviour. So these are the kind of nice, simple ones, but there's a whole world out there of different types of behaviour that can happen as well. Okay. So that's some background. And I just want to quickly summarise the sort of first part of the work we did, and then look at what we've been doing more recently. Okay, so when we first started talking about these, the real aim was to try and understand what was going on inside these simply connected one-ring domains, because once you start looking, you can see that all kinds of different behaviours might be possible, and we know we have this really good description for the simply for periodic and for multiply connected ones. But what could you say anything about the simply connected ones? So we ended up getting 2 classifications by studying them in 2 different ways. So the first way is with regards to hyperbolic distances between pairs of points. So if you take 2 points in your one domain and then you follow them along, and you look at the hyperbolic distance between the images of that pair of points. So you're taking 2 points which they map they have distinct orbits, so we're not interested in points that map together, but they stay apart. But what happens to the hyperbolic distance between them? And if you just take one pair of points, then there are three possibilities that the points can get closer and closer together, arbitrarily close together. The hyperbolic distances always shrink or stay the same, so they might get closer and closer, but always stay a positive distance apart, or they might, after a finite number of steps, they might stay the same distance apart. And the interesting thing is that what happens for one pair of points must happen for all pairs of points. And this isn't true more generally. This is just simply connected entire ones. So Gustavo will talk about more interesting things that can happen in other situations. But for the simply connected for entire functions, then we get these three possibilities. So the contracting case, when all the points, any two pairs of points, the distance between them when we iterate will decrease to 0. The semi-contracting case, when it will decrease but stay a positive distance apart. And then this eventually isometric case, when things like if you have a sort of wandering Ziegel disk, then that was going to be eventually isometric. The contracting case is if you have like a wandering attracting domain, and actually a wandering parabolic domain as well. This semi-contracting case we proved exists, but none of the examples that were out there had this type of behaviour. So that was the first classification. The second classification was with regards to the distance from the boundary, and the distance from the boundary you could define it different ways, but and you get the same classification. It doesn't really matter what definition you take. But if we take the Euclidean distance to the boundary, again, each point can get closer and closer to the boundary. It could go towards the boundary and come back in, or it could stay away from the boundary. And again, you get the same type of behaviour for all your points in your wandering domain. So you have this away, so that the points always stay away from the boundary. So things like a wandering attracting domain would be like this. Bungee, I realise this is slightly different use of bungee to the one that Dan had yesterday, but it's similar in the sense it's going out towards the boundary and then it's coming back into the middle, out towards the boundary, back into the middle, and then converging. So the bungee is nice for that because it gives you ABC. But so this is the point, all the points inside are converging to the boundary of your wandering domain. So this was the sort of first part of the work that we looked at together, and then as I say we get these 9 classifications. Okay, so this is, if I can get onto that. Okay, so because you've got 2 different classifications, each of which has 3 cases, if you put that together you get 9 different classes. And then the interesting thing was that all the examples that were out there just belong to 3 of these classes. So then you have this question, well, do these other 6 exist? And then one of the things we have is giving a technique which gives you examples of all 9 possible types. So they do all exist. You do really get this sort of rich behaviour, much more than just you get from the wandering periodic Fatou components. And then more recently, Basso and Phil and myself have looked at what happens when you have oscillating ones. And this is, say, more intricate to try and construct examples, but you can get all 6 possible types of oscillating simply connected wandering domains. There's 6 because you can't, if you have to keep on coming into a boundary part of the plane, you can't stay away from the boundary. You're going to at least have a subsequence which gets closer and closer to the boundary. So this is the sort of background and what happens inside the wandering domains. And what I really want to talk about is what we've been doing for the last sort of year or 2 through lockdown and over Zoom, is looking at what happens on the boundary of these simply connected wandering domains. And in particular, how does the dynamics of boundary points relate to the points, the orbits of points inside your wandering domain? Can we say anything about this? So Anna was talking yesterday about a case of that for a Baker domain, and so there's lots known about the relationship for periodic components between orbits of boundary points and inside, and there's ongoing work there. But for wandering domains, there's really very little known about this. So what can we say? Okay, so actually, when we started proving results, kind of the more we looked at things, the more we realized that actually we often weren't using the fact that these were wandering domains at all. So lots of our results we actually end up proving in a much more general setting. So lots of results we prove in this general setting of non-autonomous dynamical systems. So we have a simply connected domain U here. So this could be a wandering domain, but actually it could be any simply connected domain. And then we're going to map that forwards by a map F1. So that's going to go to U1 and so on. And then we have a map Fn here that maps to a simply connected domain Un, and we keep going. So I say we could think that this is more general than the case when we have our wandering domain here, U, and then each of these, this F1 is the same function at each stage, but we could do this more generally as we have here. And then we're going to call this map going from U to UN, we write as Fn. And the only condition which we put on these, which I'll just assume for the rest of the talk without writing it, is these simply connected domains, they shouldn't be equal to the whole complex plane. So they're proper subsets of the complex plane. But lots of the results which we can prove for wandering domains that actually hold in this much more general setting here. And then having got this, we then realize, well, actually, for lots of the results, these intermediate steps, we don't really need them. So we could just look at the situation when we have U maps to UN under this capital Fn here. So the more you look, the more you realize actually you don't need the fact that things are wandering domains, and then you don't actually need the fact that you have compositions, although some results you do need. It is important that you have compositions. Okay, so and I put this note at the bottom. So for wandering domains, obviously your function is well defined on the boundary, and everything's nice. But if we're looking at this general situation where we've just got a simply connected domain U, then we need to think about whether our function can be extended out to the boundary or not. And we use the idea of a radial extension to extend the definition of our function to the boundary of U where we can. And I'm going to fling that in Phil's direction, so he's talking next, and he'll say a little bit more about what we mean by a radial extension and how we do that. But I say for wandering domains, we don't need to worry about this. Our function obviously is defined on the boundary, and it's all nice. Okay. So this is, we can extend it here, and as I just said, we can actually extend it. We can, lots of results hold in this very general setting where we have, we just have a simply connected domain U, we miss out all the intermediate steps, and we just say we've got analytic map Fn mapping to this domain UN. And we don't have any link between the capital Fn and capital Fn plus 1. It's just a sequence of maps. The first thing is, if we look at what the behaviour inside these domains in this much more general setting. I said we had this classification for wandering domains. So the second classification, which I gave with respect to the convergence to the boundary, holds in this very general setting. So even though we've just taken a sequence of holomorphic maps, we actually get that all the points go to the boundary, or they all stay away, or they all bungee around. The other classification with respect to hyperbolic distances, that holds for compositions, but it doesn't hold in general for sequences. And partly if you've got a sequence, so for the compositions, your hyperbolic distance will decrease or stay the same, because at each stage you're applying an extra map. For sequences, that doesn't have to be the case. But it does hold for this for compositions. Okay. So well, when we're thinking about what results can we prove, so one place is to look is the kind of this special case when you look at iterates of holomorphic self-maps of the unit disk. So we have unit disk D, and that's, we're going to map that under F to D, and so on. So this is a case that has been studied by lots of people, and it's a good place to look and say, okay, well, what results are known in this case, and do they hold in this more general setting, or maybe you get differences, and so on. So yeah, I was thinking in some ways this looks like the wandering domain setting, in that you have the same map F applied here, but you have this there's a very big difference in that here we have the same domain, and the wandering domains you've got very, your domains are all different, and therefore essentially you're looking at a different map. The map between the first pair of wandering domains is going to be very, very different to the map between later on in the orbit. So it really is very, very different to this situation here. Okay, so sort of classic result about iterates of self-maps of the unit disk is the Denjoy-Wolff theorem. So that's if you have your unit disk here, then all the points are going to, when you keep on applying your function f, they're all going to converge towards a particular point. So either inside the unit disk or perhaps on the boundary of the unit disk. But everything converges together towards this limit point, the Denjoy-Wolff point. So as I say, one of the important things here is that all the interior points have the same limiting behavior. They all converge together. And in the situation that we're looking at, that's not the case. Even if you have wandering domains, it's not true that all the interior points converge, get closer and closer together. So that's, you might have this semi-contracting case where the points are staying a definite distance apart. But we do obviously have lots of examples when the interior points do converge together. So let's think about that. So that's obviously true if they're contracting. But also, interestingly, that if you have one interior point which converges to the boundary, so we have our one domain here, and you know that one interior point is going towards the boundary, then actually all the interior points do converge together. So even though the hyperbolic distances might not be tending to zero, the Euclidean distances will be tending to zero. So we have this result here, which says that you have one point going. So earlier I said we had this classification with respect to the boundary, which said that all the points went to the boundary, but actually you get more than that. You get that all the points tend to go closer and closer together as well. And again, Gustavo has a sort of related result in a different setting. Okay, so now we do have a situation where all the interior points are converging together. And then what we were interested in is, okay, so the interior points are getting closer and closer to the boundary, they're all converging together. What can we say about points on the boundary? Do we have boundary points that have the same limiting behavior as all these interior points? So this is really one of the sort of the key questions that we're interested in that I want to talk about. So you've got all the interior points going closer and closer together. What happens to points on the boundary? Are there points on the boundary that have this same behavior, and how many points? Okay, so because that's what we're interested in, I'm going to call this the Denjoy-Wolff set, sort of motivated by the Denjoy-Wolff theorem. So it's in the Denjoy-Wolff set if you've got, so it's a point on the boundary, so I've got if it's well defined, which for wandering domains we don't need to worry about, and it's a point on the boundary which when you iterate it, so when you apply your sequence of maps, or in your wandering domain, if you keep on iterating your function, it has the same limiting behavior as all the interior points. So we're assuming that all the interior points converge together, and we want to look at this set of points on the boundary that has the same limiting behavior. And if we look at the classic case when we have iterates of the unit disk, so we know that everything, if everything is tending towards the boundary, then it's tending towards this Denjoy-Wolff point in that classic case. And actually you can show that your function, you can define an extension of your function to that boundary point, and it would be a fixed point. And so the Denjoy-Wolff point is in the Denjoy-Wolff set in the classic iterates of holomorphic self-map of the unit disk situation. So in that classic situation, we know that the Denjoy-Wolff points in the Denjoy-Wolff set, but there could be other points that are also got the same limiting behavior on the boundary. And we want to know in general, what does this set look like? Okay, so if we look at the size of the Denjoy-Wolff set, the first question is, well, is it always, are there always points in it? We've seen there are for iterates of self-maps of the unit disk, but the first thing we have is that actually in this general setting, it can sometimes be empty. So you can have all the interior points converging together and they're converging towards the boundary, but no boundary points have the same limiting behavior. So we have an example with the sequence of Möbius maps. So they're defined like this. So we've got Fn of 0 is mapping to An, and we set up the An tending to 1. So that means that we've got our unit disk here, and we have 0 is mapping to A1, A2, and that's all getting closer and closer to 1. So that's going to tell us that all the interior points are converging towards 1. But actually what we're going to show is that none of the points on the boundary converge to 1. And in fact, not even 1. So 1 is not, and all the points around there, they keep on getting mapped well away from 1, even though all the interior points are getting closer and closer here. Okay, so all the interior points are converging to 1. But if we have this situation, so that the sum of this 1 minus an is divergent. So the 1 minus an, I should draw my picture again. Okay, so I have these points going in here. So these are the ans going in here. So 1 minus an is the distance to the boundary. So if if these points are going in sufficiently slowly that the sum of these distances is infinite, then we can choose values of lambda n so that no points in the boundary converge to 1. And actually it follows from later result, but if this sum is convergent, then actually almost all points will converge to 1. And I'll just say quickly here what we do. So basically what we do is we cover the unit disk with lots of arcs of length. So this is an arc of length 1 minus a1, then we take an arc of length 1 minus a2, and so on, 1 minus a3. So we get lots of arcs. They're all sort of supposed to be joined together, just like this. And then because this sum is divergent, we can just keep going around like this forever and ever and ever. And then each of these little arcs here, so this arc, the nth arc here, we map basically to this bit over in the left half here. So this will go over to here under Fn. And that means that any point on your unit circle here is going to lie in infinitely many of these arcs here. So infinitely many times when we apply Fn, it maps over to the left half here. So it's well away from 1. So it might keep on going near 1, but we know that it's only infinitely many times it keeps on getting mapped well away from 1. And we can settle that up even though all the interior points are going to 1, as long as we've got this sum being divergent. Okay, so that's an example to show it can sometimes be empty, but what can we prove in general? So again, if we go back to sort of classic case of self-map to the unit disk, in particular if you have an inner function, so this includes all the Möbius functions, Blaschke products, you have a sort of radial extension almost everywhere. So they're nice functions. And then have this really, really nice dichotomy, which follows from Dr. Aronson and then During and Manier, that gives you 2 different cases. And the first case, so this sort of related to the example I just talked about in a way, but if you have your unit disk, and then you look at the images of 0 under your function here, and saying if this sum of 1 minus Fn of 0 is convergent, so that's telling you that Fn of 0 is approaching the boundary and it's going sufficiently quickly that when we look at the sums of all these distances here, the distance from the boundary to this the nth iterate, the sum of those distances is finite. So it's going quickly towards the boundary. Then what their result says is that actually almost all points on the boundary have the same limiting behaviour as all the interior points. It converges to the Denjoy-Wolff point. So as long as your interior point is converging fast enough, nearly all the boundary points will have the same limiting behaviour. And then conversely, they have that if your interior point, well, either it's staying away from the boundary or it's converging to the Denjoy-Wolff point on the boundary slowly, so that this sum is divergent, then you have the sort of complete opposite behaviour that almost all points on the unit circle, their iterates are actually dense in the unit circle. So they're not converging towards the Denjoy-Wolff point. In fact, far from that, they have these dense orbits. So you get these 2 very, very different types of behaviour depending on whether this sum is convergent or divergent. So just to summarise, if the interior points converge the boundary quickly, then the Denjoy-Wolff set has full measure. Almost all points on the boundary have the same limiting behaviour as the interior points. And otherwise, it has 0 measure. So this is a sort of subset of the result, but this is the key thing that we're interested in. So points go towards the boundary quickly, and we have full measure. almost all points on the boundary do the same, and otherwise almost no points on the boundary do the same. Okay, so the proof of this result, when you look at it, I'm not going to talk about it, I'm again going to throw that at Phil to talk about next, that to prove this result about the part A, which was the points going quickly, then almost all points on the boundary do the same. When you look at the proof, it's a result about inner functions, which is usually known as Lerner's lemma, and they also essentially use sort of the first Borel-Cantelli lemma, and that offers some hope that you might be able to generalize it to a more general setting when you look at the proof. The second part, they use the Poincare recurrence theorem, which is definitely about iterates. Kind of now we're not looking at iterates in our situation here, so that looks trickier to generalize. As I say, Phil will talk about this in his talk. Okay, so I will talk about I will say what the results are, and then say Phil will talk about the proofs and things. So after a cup of coffee. Okay, so what we do have is that the first part of their result, first thing we do is we can generalize it to sequences of inner functions. So their dichotomy looked at iterates of inner functions. So we have this result here that if you don't have to have just repeated self-maps of the unit. You're not looking at the same map over and over again, iterating it, but you can just have any sequence of inner functions from the unit disk to itself. And as long as we know that the zero is approaching the unit circle sufficiently quickly to make this sum divergent, then we get the same result, that almost all points on the unit circle have the same limiting behaviour there in the Denjoy-Wolff set. So we do have this result going through exactly as you expect. The first, this bit about points going towards the boundary quickly, then almost all points on the boundary have the same limiting behaviour. So that's when we restrict ourselves to looking at self-maps of the unit disk. What about if we look at more general functions when we're looking at just one simply connected domain and mapping to a different simply connected domain? We're not restricting ourselves to the unit disk, and that's what we interest for wandering domains. Obviously, we want to be able to do this in this more general setting. Okay, so if we had this more general setting and we're mapping a simply connected domain to another simply connected domain, then the hypothesis that we had here, this was the distance. We take a point in the middle of our zeros in the middle of our first one. So we're taking a point Z0 in U, be the analog of that. We look at the images of that under Fn, and then we look at the distance of those images from the boundary of the domain that we're mapping into. So that's exactly what we have here. This is the distance of Fn of 0 from the boundary of the unit disk. So in our situation here, we'd look at this distance of the image from the boundary of UN, and then the hypothesis would be that the sum of those distances is convergent. Okay, and that would be the same here. You might hope that if you had that, then you might get almost all points from the Denjoy-Wolff set. Actually, it's not quite as simple as that. So what you have to do, you have to modify this depending on the geometry of your domains. So the unit disk is obviously very, very nice, and but in general you might have these domains could be very, very wiggly and things, and we need to modify this depending on the geometry of the domains. So what we do get in general is that we get basically the same result, but we have to put this power of a half in here. So we've got this power half here where you had 1 in the sort of classic ADM dichotomy. So we're still saying that if you have points going towards the boundary sufficiently quickly, where sufficiently quickly means that this sum is convergent, then almost all points in the boundary have the same limiting behaviour in the Denjoy-Wolff set. So for a general wandering domain where this is a wandering domain, this is the result you could apply. And if you know something about the domains and the geometry that you're looking at, then you can actually say something more precise about what power you have to take here. So if these are all disks, you can just take this to be 1. And again, Phil will talk more about that and tell you how this power depends on the geometry of the domains that you're looking at. Okay, so we do have an example where we look at self-maps of a cardioid, which show that you do this power of a half you do sometimes need. So the cardioid is kind of the sort of extreme example of the geometry where you need to take a half kind of, and you can't take one and you can't take anything less than one. Okay, so we have, this is actually the cardioid that we have is actually the sort of main cardioid that you get in the sort of Mandelbrot set. So this is a quarter here. So we construct these self maps, which they're converging, all the interior points are converging to this point here. So all the interior points converging together there, but we can show that the Denjoy-Wolff set has 0 measure, so almost no points on the boundary are converging towards a quarter. We look at the sum of these distances. We can show that if we take the power a half here, then we get that sum is divergent. If we take any power less than a half, it's convergent. So if the result was to hold with some power less than a half, you get a contradiction. So you really do need to be able to take this, the power does sometimes need to go to a half. And this example, again, it would come from Phil's talk, but we start off by looking at an example of mapping a unit disk to itself, and then we map the unit disk to the cardioid and sort of transfer it across there. Okay, so that's been sort of positive results, saying that if you have your interior points going sufficiently quickly, then almost all points on the boundary will have the same limiting behaviour. But what about the opposite? If the interior points are going slowly, so that sum is divergent, what can we say about the points on the boundary? So this is our general situation. We've got simply connected domain mapping to UN. Supposing that these distances of the interior points to the boundary, the sum of these distances is divergent. Then if we had an analogue of the ADM dichotomy, then that would say that the Denjoy-Wolff set had 0 measure, so that almost no points on the boundary had the same limiting behaviour. We don't have this true in general, so we can give you examples which satisfy this hypothesis that this sum this sum is divergent, and yet the Denjoy-Wolff set. So here it has full measure, so it's a composition of Möbius maps, and even though this sum is divergent, the Denjoy-Wolff set has full measure. There you might say, okay, well, then Möbius maps, they could be special. So, but we also can get an example of compositions of degree 2 Blaschke products. So this is a semi-contracting case for which the Denjoy-Wolff set has positive measure. At the moment, we don't know if it has full measure. We know it definitely has positive measure, so it doesn't have 0 measure, which is what we might be hoping for. But we do have another example. Again, it's compositions of degree 2 Blaschke products, but in this time they're contracting. So the interior points, the hyperbolic distance between pairs of points is tending to 0. And for this example, we can show that the Denjoy-Wolff set has 0 measure. And actually we get the strong result like the ADM, then we get the orbits of almost all boundary points are dense in the unit circle. And so one of the things which this raises is, can we prove a generalization of this dichotomy if we restrict ourselves to look at contracting compositions? And again, Phil will talk about all this in more detail, and you'll see that even this one example is actually quite complicated to kind of prove that you have this result here. But one of the interesting things which Fatou pointed out was that if you go back to the ADM dichotomy and you look at the condition there, then actually when you're restricting yourself to these iterates of inner functions, if this sum is divergent, then they must be contracting. So it's kind of quite reasonable to kind of put this hypothesis on that what happens if we look at contracting compositions. Okay, so that's the kind of lots of the stuff we've been looking at. I'll just give a quick summary of what I've said so far, and then just a couple of slides to finish up with, which will lead into Vasso's talk as well later. So what we've been looking at is kind of maps, holomorphic maps from between simply connected domains, and that we think certainly this could be a wandering domain mapping to along an orbit. And we had that if you have one point inside, say your wandering domain approaches the boundary as you go along, then all the images of all the interior points converge together. And then we had this part, this ADM dichotomy, that if the point inside approaches the boundary sufficiently quickly, then almost all the boundary points have the same limiting behaviour. But conversely, if it approaches the boundary more slowly, then there's lots of different types of behaviour that can occur on the boundary. Okay, so that's a very quick summary of what I've just spent time talking about. I just want to finish with a couple of slides which talk about, well, this one's talking about the opposite way around. So far we've been saying, okay, suppose we know something about the points inside. What does that tell us about points on the boundary, and how do they behave? Okay, now let's think about the other way around. Suppose you know something about the boundary and how points there. Does that tell you something about what's happening inside your wandering domain or in this more general situation? Okay, so let's suppose we've got our sequence of maps, and I've put here, so we've got a sequence of maps going from U to UN, and we've got a point here which is on the boundary, and it maps to the boundary at each stage. Now for wandering domains, again, that was always the case, kind of, but we're just going to specify that in this more general setting. And then we're going to look at this set here. So we've got one point on the boundary, and we're following its orbit. So this is the point zeta naught. And then we look at the set of points, all the other points on the boundary which have the same limiting behaviour as this one identified point that we took. Okay, and then basically the result we prove is that if that set is large enough, if that set has positive harmonic measure, then all the interior points are going to have the same limiting behaviour. So if you have enough points on the boundary which all converge together, then they're going to drag the interior points with them. So that's basically saying that this set, as long as it's big enough, then it will be in the Denjoy-Wolff set. It's got all the interior points have got the same limiting behaviour as it. And then the very last thing, which Fatou will talk about in her talk later. So if you, again, we talked about earlier about if you have contracting compositions, and then well, certainly for some types we could get stronger results. And one thing which we can show for contracting compositions, if you have contracting compositions mapping the boundary to itself, which is obviously the case for wandering domains, then we can show that this Denjoy-Wolff set either has zero or full measure. And I say I won't talk about that. I'll leave that to Fatou, who's there with you, and she'll talk about it later. So that's a sort of quick overview of where we've been, and then as I say, the other talks will give you some more of the details, which I was the lucky one. I just got to tell you what the results are, and the others can tell you how the proofs go and some more about them. So thank you very much.
Thank you, Gwyneth. Are there any questions or comments from the online audience?
Gwyneth, in your example,
Yeah.
you have this example of the where you have the exponent 1/2, and you show that that's kind of best possible. Is it? Sorry, could you go back to the slides on that one?
Yeah. Let me see if I can get back on that. I saw a cardioid go past somewhere. Yeah, this one.
Right, so they're all cell phones with the same cardioid. Is it? I mean, is it this essentially? So how do you do this? Do you take a sequence of maps of the circle where it's kind of critical, and then you use the asymptotics of the conformal map to the cardioid to conclude, or how exactly does it work?
Yeah, I think Phil might say something in.
Okay.
Unfortunately, he's not the internet was so dodgy that we decided only one of us should join in at a time. But yeah, so we sorry, my slides are randomly going up and down. This is very weird, but okay, I've pressed the button too much. But yeah, we take self maps of the unit disk, and you take the remapping that maps the unit disk to the cardioid, and you can just transfer it all across. So you set it up in the unit. In fact, this is an example which we needed for another, which is useful for something else, and then we realised we could actually transfer it across, and it was helpful as an example in this setting. But you set it up in the unit disk that everything's tending to, the interior points are tending to 1, but that almost nothing on the boundary is tending to 1, and then when you transfer it over, it kind of carefully, it all goes through to this cardioid setting.
Okay, thank you.
Any more questions? Well, otherwise, let's thank Gwyneth again.
Thank you, and I'm glad my internet survived after that.
Yes.